Today we have Jasper talking to us about an introduction to Krylov complexity.
Yeah, thank you. Hello, everyone. Good morning and good afternoon. Um, so today I am going to talking about complexity in general. So we'll be talking about operator growth and how complexity can be quantified. So before we start, I'll just like to go through content. Firstly, I'll start with a kind of a physical intuition of what do you mean by operator growth, and then we'll move to a very early concept of quantifying this operator complexity, and then we'll move on to more robust form of quantifying complexity known as Krylov complexity, and we'll move on to like these implications on holography, and then to my current very latest research. Yeah. So what do you when we say what do you mean by operator growth? So firstly, usually what I would like to do is like to imagine a water surface, right? We have a water surface, and if I make a certain a delta function, a dent of maybe a delta function, it's going to make a dent, and then the water is going to, after a certain time t, there's going to be some wave on the water, right? So initially, how we can visualize this as initially our operator is very simple. It's just a dent in a single point, and it has evolved over time. The surface of the water has evolved over time, and after certain time, to make the exact form of the water surface, we need a very complicated operator in this case. The operator to form this surface is very complex now. So this is what we mean by operator growth. The operator grow from a very simple operator to a very complex operator as we move along time. So in Heisenberg picture, we see that the time evolution is given by this equation, and we can expand this equation with the nested commutator form and write it in this form. This form is actually very important for us in the later Krylov part, because we are going to derive some form of basis of a space from these nested commutators. Yeah, but for now, the idea is simple. The operator starts from a simple operator. It translates along time, and it becomes complex over time. Yeah, that's the whole idea. So around 2005, I believe, Nielsen and his colleague comes up with an idea. This idea comes from the question in quantum computers, I believe. They were asking these questions of what is the minimum amount of circuits that we need to like these small gates that we need to form a quantum circuits. Like what is the minimum amount that we can have? So their idea is to recast the entire problem into some kind of a Riemannian geometry. And from this geometry, technically what we need to do is we need to find the shortest path. So once we find the shortest path, and the length of this path will be defined as this complexity. But this definition has some shortcomings, such as there is something arbitrariness about this definition. So yeah, we'll come to it when we get to it. So firstly, what they define is they define a Schrodinger equation for every unitary operation in the circuits. So the Schrodinger equation looks like Yeah, as we can see that this is our very simple Schrodinger equation, and U is our unitary operation. They were saying they were trying to isolate this gates, which is formed by a single qubit or like one or two qubits, because if we try to control more qubits, it's going to be much harder. So the question was, can we form a path with just a combination of this lower number of qubits? So here C naught is a gate. It's called control gate, control not gate. So what it does is, this is a 2 qubit. I made a small error. Fine. 2 qubit gate. So what it does is, it has a target gate. Let's say C naught acting on 0 and 1 will give 0, 1 unchanged. This is called our target control gate, and this is our target, right? So if our control gate is 1, then our target gate will be flipped by C naught. So yeah, this C naught and Hadamard gates are very simple. Hadamard gate is much more simple than C naught. Hadamard gate is just 1 qubit gate. All right, but I wouldn't go much into it. So this to come into the idea of this Riemannian geometry, we need to understand in what kind of space do these qubits lives in. So I'm pretty sure most of us are aware these qubits, they lives in SU2n symmetry group. So this SU2n symmetry okay, before we get into it, if we have for 1 qubit, we have 2-dimensional space, right? It's spanned by, or this is, let's say this is 1, and this is 0. Spanned by 0 or 1. For n qubit, it's going to be 2D space tensor multiplication, 2 tensor multiplication n times. So which is 2 in space. So the dimensions of our space, the group that we are actually working is SU2n, right? So yeah, that's a group that we care about in this mathematics. So this SU2n is also a manifold, differentiable manifold. It looks like our usual space and time. It can be twisted, and it can be warped, as we can define certain metric on this manifold. Yeah. So yeah, now we are going to see one property of this one. I shouldn't say choice made by Nielsen's. It's not really a choice, but it's kind of his. But let me just explain it a bit. So our Schrodinger equation gives. So in order to get our Hamiltonian, we need the Schrodinger equation needs to be right invariance. So this will give us our Hamiltonian H of S, right? So going along with right invariance, we'll make sure that the cost that we are going to define on this metric is independent of whatever the gates we have applied previously on our state, right? So this is the choice Nielsen's made in order to make sure our cost doesn't like climbs up for simple circuits, also for complicated circuits. We want to differentiate between simple circuits and very complex circuit. That's the idea about this right invariance. Of course, we can also take for left invariance, but yeah, with the left invariance, our Hamiltonian is going to become our new Hamiltonian is going to become like U dagger IQ. So this is more of a Heisenberg picture. What it does is, if we want to assign some costs in this picture, we are going to add up all the cost of all the assigned gates in the past. So we don't want to do that. We want our cost of our current gate to be independent of whatever we have done in the past, right? So that's the idea of the choosing right invariance in Nielsen formulation. So yeah, let me just yeah, right. So before we move on, I would just like to explain what is Pauli strings. So we have this Pauli matrices. So Pauli matrices is for one qubit system. These are X, Y, or Z. And also, of course, but I wouldn't count this for now. So we'll call this X, Y, Z. So for multiple qubit system, let's say for n qubit system, we will have the new Pauli matrices. Pauli matrices will be tensor product of all these matrices, such as X tensor product, Y tensor product, Y tensor product, so n times, right? So the combination of all these new matrices are, well, we call it Pauli strings. So Pauli string is going to span all our gates. Pauli string can explain all of the gates that is available in this SU2N manifold, right? So what we can do is we can recast our Hamiltonian in terms of this Pauli matrix. And here OI is the Pauli strings. We now call it strings, not matrices. And YS is some weight function of each Pauli matrices that depends on where we are in the manifold, right? Right. Let me just remove this for now. So the Riemannian matrix that Nielsen's defined looks like this, d square. B square. And from here we can define we can define our Nielsen's complexity as C equals to minimum of yeah, as you can see, this is our the minimal. Oh no, I wouldn't say minimal. shortest path. So we're just searching for the length of the shortest path, and we will say the length of this path is a complexity of whatever the unitary function that we wants to perform, right? So this is Nielsen's complexity, and we can see here our this matrix Zij is very arbitrary. We have to, in Nielsen's complexity, we have to know what is costly, what is a costly gate, and what is not a costly gate, right? So a costly gate will be like 15 qubit system gates. This will be very costly to make this kind of gate. And what will not be costly is like 1 qubit, 2 qubit gates, like this C naught and a Hadamard gate. They are not costly. So we'll assign very less value for these non-costly gates, and very expensive numbers on these costly gates. So, but at the end of the day, this is still arbitrary. We can assign any value, whatever value that we wish. So this will be kind of a bad news for us, because we don't want this kind of arbitrariness to come in between this complexity later on. I'll come to you later on. So,
Hey Jasper, can I ask a question? So if you go back to the top slide, the slide above,
yeah.
How did you get the metric? So when you're defining your action, you write it as like a sum over the diagonal terms.
Yeah.
So how does that happen?
Can you repeat that again?
So instead of it being sum over ij, gij,
yeah,
etc., how did you get it to be the sum over the diagonal terms?
Oh, right. Wait, let me. Wait, I'm not sure. I don't have the answer today right now, but yeah. Can I get back to you after a while, maybe?
Yeah, sure, that's okay.
Yeah.
Just one other question. Can you remind me? So wait, is the yi's, those are the tensor, that's the tensor product of the Pauli matrices, right? So they're the basis elements.
Yes, these are the basis.
Okay. I'm just curious, like what does it mean when you say like take a square root of these basis elements? Like what does the square root mean in this context?
Yeah, so about that, I am just going into an example.
Oh, good. Okay.
I thought you'll be good for it as an example, right?
Nice. All right. Thank you.
So with tensorial product, I'm not sure how we'll do mathematics on this.
Oh, so is this more like a formal approach at the moment? And then
yeah,
the
this
idea
is
to
like
do it
very
formally.
formal approach, yeah. Yeah,
Okay.
yeah, this is very formal approach, but yeah, so I want to move on to one very simple example without doing all this tensorial product. Okay, where's my example? Right. So we have a 1 qubit system. Right. So our qubit system is spanned by either 0, 1, or if you prefer, say 0, 1. Our system is spanned by these two, and the generators are these Pauli matrices, right? So to make it easy, we will define the penalties or the matrix. Here we have defined zxx and zyy as 1, and zzz as k square, where k is much greater than 1. Well, you should aware that this example is just an example. I don't know how it will apply to any other real life applications. This is just to show that how everything works or whatever we have discussed to an extent, right? So so the situation that we have is we have if we have to imagine, we have a three-dimensional sphere, right? We have a three-dimensional sphere. We can call this X, Y, and Z, right? So what we want to do is we want to go from our initial our like whatever state we are in the beginning, our initial state, to some unitary operator, which we'll call it utarget. And utarget is defined as, so what it's saying is we want to move our sphere an angle theta around z axis, right? We just want to move this a sphere around z axis. So what we can do is case one is we can just directly rotate the entire sphere around z axis without caring for how costly it's gonna be, like, right? We'll just move let's say direct rotation of z axis, right? Now, if we do this, the cost is going to be and this is going to be rotated by theta by 2. This is our cost from our previous definition. And this is just k theta by 2, right? This is case one. And the case two, there is another way that we can go about this problem. We do not rotate about z-axis, but we rotate about x and y-axis. So how we can do that? We can start with a rotation on x-axis by minus pi by 2, and then rotate y-axis by theta, and then rotate x-axis again by pi by 2. This will get us to z rotation of theta. This can be done, right? And the cost here is going to be, it's going to be just zxx, which is just 1 multiplied by pi by 4 plus 1 multiplied by theta by 2 plus 1 pi by 4. So this is our cost, and this is just going to be pi by 2 plus theta by 2. So we can see for k much greater than 1, much greater than 1, we can have this, the cost is much greater than this cost of combination of x and y.
Wait, so just to ask about this one,
Yeah.
when you're summing up the costs, is
Yeah.
this because you're doing them independently? You calculate the cost
Yeah,
of the first
we are
operation.
taking this independently. Yeah.
Okay,
So
okay.
yeah.
I see.
Yeah, it's an
That makes
independent
sense.
rotation. So yeah.
Yes. Do you know how you would do to sum if you rotated both x and y at the same time? Actually, no, that doesn't make sense, but
No, yeah, this is, you can do rotate at the same time, right? Even if you rotate at the same time, you're just gonna be adding up. because anyway the rotations are independent of each other, if that makes sense. Like it is the same with rotating x first and y first, or y first, x first.
I see.
Yeah. Okay, yeah. So we can see that some path is much more expensive, and some path is less expensive. So we will choose a path which is less expensive, and then what is the cost or the length of the path as the complexity, the circuit complexity. Yeah, that is how we define. This is a very early form of complexity definition, but as we can see here, the metric ZZZ, ZXX, they're arbitrary in nature. We can define anything that we wish. It's not controlled by anything, right? It's arbitrary. Now also, as I think I've said before, the idea of Nielsen complexity also relies on idea of locality. Locality means we want to know what is our what do we mean by two states, one state, two qubits, one qubit, three qubits. We have to know this thing, which one is easier to build. But in general, QFT, we don't have such kind of definition to us, so we cannot. It will be very difficult for us to define what do we mean by this metric, right? How do we define this metric for each point? Well, we don't know how to do this, and also Nielsen's complexity kind of ignore how operator actually evolve over time. We're just finding the shortest path. We don't care how it actually evolved. So we need more robust complexity definition where we employ our own kind of Hamiltonian to like generate this some intrinsic property of the system, right? So that's where Krylov complexity comes in. So we can see at the beginning our operator or operator at time t is defined by our original operator minus, is it minus? No, plus I commutator between our Hamiltonian and original operator minus, sorry, this is not I. T squared by 2 factorial and so on, right? So this was our Heisenberg picture. So from here we define a super operator which is called Liouvillean here as defined. Liouvillean is whatever Liouvillean O will be defined as H1, right? With this definition, we can recast our entire operator in this form, in a very neat form, concise. So as we can see from this expansion, that our operator at time t is made up by just these nested operators, right? Our operator at time t cannot go beyond this nested operators. It has to somehow linear combination of these nested operators, right? So this means our operator at time t does not explore the entire operator Hilbert space, right? So it just explore some subspace of this operator Hilbert space. So and this subspace is spanned by all these nested operators, right? Because this operator at time t is just linear combination of these nested operators. It cannot go anywhere else. Right. So we have this certain subspace. Before we move on to anything else, I want to define a certain inner product in this operator Hilbert space. So here we'll be defining this inner product. What is that name? Yeah, sorry, I forgot what's the name of this, the definition, to define this inner product. So we can see the expectation value in statistical mechanics. Expectation value of a operator is given by trace of the operator multiplied with this density function, right? So to define at infinity, for very large temperature, we can see that that is trace of beta h. So for very large temperature, beta goes to 0. So z just reduces to trace of identity. So this is just a dimension for Hilbert space, right? So for very large temperature, z boils down to the dimension of Hilbert space, and we can define the inner product like these are two operators. So I'll say cat. It's defined as 1 by the trace of a dagger, of course, cat. Right. This is our definition. This is for like very large temperature, and it has come to my attention that in certain QFT system, sometimes this defining this inner product at infinite temperature seems to be problematic. So there are ways to define it certain finite temperature. It's just a So I'll just write down how to define it. Finite temperature is z of function of beta, trace of beta Hamiltonian by 2, a dagger minus beta h by 2, b dagger, right? This is a definition for finite temperature, but for most cases, infinite temperature inner product should do. This is for finite temperature. Okay. Now we have a certain subspace and we have defined inner product. Before we move on, I like to comment on if the subspace that is spanned by these nested operators, nested commutators, actually orthogonal. So let's see. So we have our original operator or not. Let's see if this is actually orthogonal to our next operator, which is Liouvillean operating on our original operator. So this is just trace of right, and this we can see is trace of yeah. So as you can see, we're using cyclic property of trace. We can see that this is just 0. So great. Two of the vector is actually orthogonal, but this is not. This can be rewritten as L squared minus of L, sorry. And this is just a norm of our operator, right? Square of our norm. So this is not zero. So although we have a subspace and define an inner product, we don't have a proper basis of this subspace, right? So what we want to do is we want to find a proper subspace to proper basis of this subspace. So this is where Lanczos, I think that's how it's pronounced. Lanczos algorithm comes in. So how Lanczos algorithm work is, okay, let's consider our original basis. Let's say this basis is 0. And let's assume that this is or not is normalized, right? Okay. Now we want to find our next vector, which is orthogonal to our original or not operator. So I can define O1 as 1 by B1 L0, Liouvillean acting on our original operator. And here B1 is norm of L0, right? This is just normalized and happen. So as I have proof above, this 2 is actually orthogonal. This 2 is orthogonal to each other. Now, if we want to define our next vector O2, we will be using a procedure called Gram-Schmidt procedure. So what it says is we act on our previous operator O1 by the Liouvillean and subtract whatever is overlapping with our new operator O2. So our overlapping is with O1. All right. So I will subtract something like B some constant and O0. Right. So this is how we define the next thing. But before defining the O2 exactly, I will borrow this as call it A2, a new vector. And then O2 will be defined as 1 by B2 of A2. B2 is our normalization. So for general ON, be defined as BN, AN. Yeah, this is how we define. And AN is defined as L acting on 1 minus 1, BN minus 1, or N minus 2, right? But you can ask me, is this, we have a set of O0, O1 to ON. You can ask me, is this orthogonal, right? Because because I cheated a little bit while defining this new basis. As you can see, for ON, I have defined 1 by BN, Liouvillean acting on ON minus 1, minus BN minus 1, ON minus 2. So you can ask me, okay, yeah, I have subtracted whatever is overlapping with our ON, right? What about ON minus 3? Or ON minus 4? Why aren't we subtracting from this? So that is actually because our Liouvillean is actually anti-Hermitian, because our Liouvillean translate our Hamiltonian, or sorry, our operator through time, right? We apply our operator on Liouvillean and generate another operator at after time t, like it's a translation. So it must be anti-Hermitian. So because of this anti-Hermitian property, we do not need to subtract all these smaller operators from us. So, but before we move on, I would just like to check that if this is actually orthogonal in nature, right? Right. So the usual Gram-Schmidt procedure to find orthogonal basis is to subtract each and every operator that is overlapping with our new operator, new basis. We subtract each and every vector from our new vector to make it orthogonal. That's the usual find. So what we can do is we have a n plus 1 as Liouvillean acting minus summation of k equals to 0 and ck. Okay. Now, in here, what we want to understand is what is the value of, how does this ck behave? What is the value of the ck's, right? Let's consider a case 1. For case 1, we are going to say k is lesser than n minus 1, right? So we are asking for k lesser than n minus 1, what is the value of ck's? So for k lesser than c minus 1, we're going to have ck equals minus L of k n of n, right? But let's look at our L of OK. Liouvillean acting on operator k. This for k lesser than n minus 1, L of k can only generate certain vector up to n minus 1 max. This L of k can at maximum generate our operator up to n minus 1. It cannot generate n, right? And from our assumptions, this will be something like some constant k or n minus 1, at best O n. So this is 0 because they are already, by assumptions, they are orthogonal in nature, right? So what about for k equals n? So for k equals n, we have Cn equals On, Liouvillean On, which is equals to minus of Lon. And this is just minus Cn, right? This implies Cn is a 0. Right. So we have get rid of from all this summation, k equals to 0 to n, ck, okay. C 0 up to Cn minus 2. They're all 0. Also, Cn is equals to 0, right? But for k equals to n minus 1, Cn minus 1 is actually On. And this is not 0. This is some number. I'll show you. So L acting on or n minus 1 will generate some constant Bn with On plus some other lower term, right? So this lower term will contain On minus 1, On minus 2, blah, blah, blah. But it doesn't matter because they are orthogonal to On. It will go to 0, right? This will be minus Bn. Whatever, yeah, not minus Bn, this is Bn. So whatever that remains is actually minus Bn On cross On. So this is just minus Bn. So what do we learn from here? Well, that we have proved two things here. This proof that our previous orthogonal, all this O0 to On, all these are orthogonal. And my little assumption that we just have to subtract our immediate neighbor, like subtracting our immediate neighbor is enough for this anti-Hermitian Liouvillean, right? Right.
Jasper, just a little bit of a doubt here.
Yeah.
So you said that we would not need to subtract, say, for On, we would not need to subtract
Wait.
On minus 2.
Can you speak louder, please?
Hi. So I was saying that when you are applying the Liouvillean to, say, On,
Yeah.
there will be zero overlap with, say, On minus 2 and N minus 3, right?
Yeah, because from our assumptions, they are orthogonal to
Yeah, so
On.
wouldn't that, and given that would mean that the overlap will only be between the immediately preceding vector, right? So for On, it'll be On minus 1 that will be overlapping.
For On, it will be?
On minus 1 that will be overlapping, right? And therefore you have to subtract that. My question is, wouldn't that condition make the Liouvillean a Hermitian?
Why?
So given that you only have to subtract the immediate neighbor and not the
Yeah.
It's not phrasing out in a sense where that the overlap extends to all the external neighbors.
No. This actually makes a Liouvillean anti-Hermitian.
Okay.
Because in this proof, we actually need the point that the Liouvillean needs to be anti-Hermitian. So it is specifically because Liouvillean is anti-Hermitian, we can just subtract our immediate neighbor.
I see. Okay.
Yeah. Okay, that's great. We have basis, we have defined an inner product. So we have a proper subspace, right? And everything, from t equals to 0 to t goes to infinity, the operator can be defined. All the history of the universe of the operator can be defined in this subspace. Great. Now, as we have this subspace, we will define what is this Krylov complexity. So any operator can be defined. We have our basis On. So now any operator of T can be defined as summation of I, some function F, and our basis OI, right? So this is what we're exactly doing. And this is our function that the weight given to any specific basis. And the Krylov complexity is defined as the average weight of our function, of our weight function, average weight of our weight function. So this is like the average position. So we can imagine this, our operators as like O0, O1, O2, O3, On. And we can say that to go from O0 to O1, we need to hop with the amplitude B1 or B2, B3, blah blah blah. This is something like hopping mechanism, I believe. So yeah, the Krylov complexity is defined as the average position where our operator lies. So the average position where our operator lies is defined as Krylov complexity. So mathematically, this is the exact definition. So this quantifies how complex our operator has become after time t. So one thing about this Krylov complexity is we can notice that there is no arbitrariness in our definition here. Every single thing is defined by our Hamiltonian of our system, right? So if we have Hamiltonian, instead of defining our in Nielsen's case, instead of defining arbitrary zxx, zyy, oh, sorry, it's lagging a bit. Yeah, here, instead of defining arbitrary metric, we actually have something which we don't have to do this. We don't have to do this anymore. We just have to set up our system such that everything that we need is from Hamiltonian. So it's intrinsic in nature, right? There's nothing arbitrary here. So yeah, Krylov complexity, as there's no arbitrariness in Krylov complexity, this can be used for any general purposes in QFTs and any operator growth. Right. So we have seen Krylov complexity and Nielsen's complexity and how they work. So I would like to come to more of my research from the holographic point of view. So in early days, around 2015, I believe, Susskind and his colleagues and Maldacena and all, they had this idea that we know that the black hole reached thermal equilibrium really fast, and also at the boundary we can see that if we keep mixing up states of the boundary, it seems to arrive to thermal equilibrium in a pretty short amount of time. But the Susskind question was, okay, we have this thermal equilibrium really fast, but what about this growing Einstein-Rosen bridge, growing volume of this Einstein-Rosen bridge, right? As time moves forward, even though the thermal equilibrium has been reached by black hole, the volume of Einstein-Rosen bridge keeps increasing with time. So the question was, what does this increase in volume duals to in the boundary, right? So Susskind's answer was, well, it's the complexity that is dual to this boundary. So in early days, they tried to study this SYK model with SYK models, and they kind of form a conjecture where rate of growth of complexity is directly proportional to the proper momentum of the particle. So what it says is we have, let's say we have our holographic radial coordinate Z, and let's say this is our boundary, the UB boundary, right, or asymptotic boundary. So what they propose is the complexity, the rate of complexity at this CFT, let's say at the boundary, the rate of growth of this complexity is directly proportional to a particle, the momentum of the particle falling inward in the geometry, right? So this is their conjecture. And very recently, like few months back, there was this paper by Caputa and his colleagues where they actually proved this relation. They actually proved this relation in an ADS3. So they have this. Where's the? Never mind. They have this Poincaré matrix, Poincare-like matrix. This looks like LADS square by the square. Sorry. Right. They prove this on this Poincare-like coordinate. How they prove is very interesting. So what they realize is the Lanczos coefficient at the boundary, the BNs, and the two-dimensional space that is felt by our infalling particle, that is T and Z. This two-dimensional the symmetry in this two-dimensional space felt by this infalling particle are governed by the same symmetry group, right? So from this, by using this idea, they actually prove this idea concretely. Minus this epsilon is some number that I won't be discussing what this is. So they actually proved this idea. So very interesting paper. So coming to my research, our question was, we have this certain geometry which is ADS soliton, and we have another geometry which we call deformed ADS soliton. So how do we deform this? We instead of the usual Poincare coordinate, we use and then this is our let's say a new, right? So this kind of space is deformed by this exponential factor. So what it does is it kind of shrink our proper volume as we goes on. So we are interested in this kind of matrix because it kind of shrink and then it can produce this something that looks like confinement geometry. Although it can goes from 0 to infinity, nothing is restricting us, but because of this shrinkage of this proper volume, it mimics this confinement geometry, right? So we are interested in this, but unfortunately, one of my collaborators requested me not to reveal too much yet because we haven't archived it. So I'll be restricting my discussions to this ADS soliton. So in this ADS soliton, our geometry actually looks like a cigar shape, right? This is our boundary. It looks like a cigar shape, and the particle is restricted up to certain z-axis, z equals to z0. From z equals to infinity to z equals to z0. It's restricted. So the value of our z0 is determined by such as mass gate of our boundary theory. But for this system, we do not have any data on what should be our z0 or what should be the value of this az, that the deforming parameter, which we put as. So z square is our radial coordinate, and we are interested in what happens if we vary this, right? So so what we do is, to find the momentum of an infalling particle, we just track what is the geodesic of a particle starting from a UV. So we have this soliton geometry, and we have a point particle like object, and we track its geodesics, right? As we track its geodesic, it will produce certain momentum P. So we want to capture what is the value of P going from this UV to IR. So what happened to this? So this is our one of the results. So as we can see, we have tracked what is Z here. This Z of T is a position at radial coordinate of a particle, and we can see that the particle is going up and down, then up and down. It's oscillatory. It's oscillatory in nature, right? So as we can see from the geometry, the particle starts from UV, goes to IR, and then it goes up to UV again, and it falls down, goes back. So this is what we are noticing here. And because of this presence of this A, we can see that our geometry is slightly deformed. As we can see, the frequency increases as we keep frequency decreases as we keep increasing A. Right. So the geometry is slightly deformed in our case. So coming to Krylov complexity, so we exploit this conjecture. We exploit this conjecture and try to determine what is the complexity from the momentum that we have obtained above, right? So this is the result that we have, the value of the complexity. So we can see that it's oscillatory as we expect from before. And with our deformation parameter A, our complexity changes very slightly for a fixed energy level, right? So why the complexity is oscillatory is because we think it's because our the dual theory in at the boundary is actually confined phase, right? For a soliton geometry, it's confined phase. So we think in confined phase, the Hilbert space is finite. So what happened is we start from a very simple operator, and then it explore all the possible area, and then it bounce back from after exploring the entire operator Hilbert space, it bounce back to a simpler operator. So it keeps bouncing back and forth. So that is why we're seeing this kind of oscillatory Krylov space. Yeah, so this is the meaning written. I've explained most of the things. So it's a confined phase in Hilbert space, so it's bouncing back and forth, right? Right. So the conclusion of our paper is so the deformation parameter A seems to change our frequency and how complexity can actually evolve in the boundary case. Our deformation parameter can affect it to an extent, right? And we can see this oscillatory nature because of the finite Hilbert space available to our operator. Yeah, that is our conclusion for now. So yeah, this is the summary. This is the last pages. So we have seen we have come from Nielsen, which has arbitrary input, to Krylov evolution. So Krylov doesn't have any arbitrary thing anymore, so we can use it for any general purposes. And then we come to idea of Susskins, and then we come to my recent paper, which will be available soon on arXiv. Yeah. So that's it. Thank you. Thank you, everyone. Yeah. So these
Thank you.
are some of the. Yeah. I hope I wasn't boring you going from 2005 to 2026.
No, this is very interesting.
if-
Thank you very much.
Thank you, Jasper.
Yeah, thank you for having me. So if it's possible, I would like to talk about this paper after we publish, because we are writing another follow-up paper. So it'll be very interesting to see some of the results. I'd love to discuss in the future.
Yeah, certainly. Yeah.
Oh, do you mean you have
Yeah,
like
so
two papers? So one Danish and then another
yeah.
one?
So
or-
we kind of have very interesting results right now. That's why one of my collaborator suggested not to reveal too much yet because we're writing another follow-up. So I couldn't reveal. I'm very sorry. I was thinking of talking just about my paper, but yeah. Yeah, thank you for having me. Yeah. So I think it's already past 1:30. Maybe we should end up the meeting.
Yeah, unless people have any quick
Yeah,
questions for
unless-
you. Yeah.
Hey, Jasper. Thank
Yeah,
you for
hey.
a very interesting talk. I just had a doubt, rather something, if you can comment on the last part of your talk.
Yeah.
So if I'm not mistaken, as the Krylov complexity will grow
Yeah.
on the boundary, it will be like the particle will be falling deeper into the black hole, right?
No, yeah. So
So
the
my
thing-
question is that that would cause it to gain the radial proper momentum,
Yeah.
right? So
Yeah.
I just want to correlate the particle gaining proper momentum to the back and forth oscillatory Krylov space dynamic you saw. That how do the two of them fit together?
Okay. Yeah. So first of all, we do not have black hole in our case, right? This is this geometry does not have a black hole. This geometry is physically cut off, right?
I see.
At the infrared region, at the low energy region, right?
Hmm.
It's physically cut off by the geometry itself. So,
Okay.
So when it reaches the IR, the tip of the cutoff,
Right.
it will bounce back because of its geometry.
So this is an external like constraint we are imposing on the natural progression of the
Yeah.
boundary.
This is an external constraint enforced by the geometry. Yeah.
Right. Okay. Thank you.
Yeah, but black hole is coming up.
I'm eager to listen to that part whenever you're done with the publication.
Yeah.